All right, in this video we want to take a look at an example of a second-order homogeneous equation with constant coefficients and solve. I actually want to do it as an initial value problem so that we'll have two initial values given as well. There's my initial conditions. So the differential equation, I got y double prime plus 3y prime minus 10y equals 0. And I want y of 0 to be 3, and I want y prime of 0 to be 4. So with these second order equations, we're going to need two initial conditions, and you'll see why. So, as we discussed in the previous video, we're going to assume that we have a solution of the form y equals e to the rt for some value of r, and I have to find r. Now, I'll admit that I'm going to write down a bunch of steps that I don't typically take, but I think for the first time we're doing an example, we should go through all the steps. The thing is, the steps are the same every time, and so you just know what to expect for the end result, right? If this is y equals e to the rt, then here's the derivative and the second derivative, and I plug them into the equation, getting r squared e to the rt plus 3r e to the rt minus 10 e to the rt equals 0. Factoring out the e to the rt leaves this. As in the previous video, we point out that the exponential can't be 0, so it must be this factor over here that's 0. Okay. And the thing is, I would generally skip all of this stuff and just write down the characteristic equation. I know I've got a second order homogeneous equation with constant coefficients. I'm going to assume y equals e to the rt, plug it in, and get down to an equation that looks like a quadratic equation with exactly the same coefficients that I had here. 1, 3, minus 10, 1, 3, minus 10, right? And the y double prime turns into an r squared, the y prime turns into an r, and the y turns into a 1, and you get that equation. The problem that I see with students just jumping straight to this line right here is that they forget that what they actually did was they assigned y to equal e to the rt. That is, they'll solve for r and then they kind of forget what they have to do with it because they didn't say what they did with it in the first place. So at least say, hey, I'm letting y equal e to the rt, and I know it leads me to this quadratic equation here, which I can then solve. This one I can factor. R squared is r and r. The 10 is a 5 and a 2 with a plus in front of the 5 and a minus in front of the 2. Two reasons to make that a negative 10 and to make that a plus 3. Right? So I get two solutions, r equals minus 5 and r equals 2, which gives me, that's two solutions to the quadratic equation. So that gives me two solutions to the original differential equation up here of y equals e to the minus 5t and y2 equals e to the 2t, okay? Which gives me a general solution. This is what we claimed in the previous video, that the general solution then would look like c1 e to the minus 5t plus c2 e to the 2t. Now we have to have that these two functions are actually independent of each other, and I know I haven't defined what independent means yet. But if you've had any linear algebra, it is the same meaning, right? If you've done linear algebra before, you know what linear independence is. In the case of two vectors, they're linearly independent if one is not a scalar multiple of the other, or they're linearly dependent if one is a scalar multiple of the other. And the thing is, you can multiply e to the 2t times any constant you want. You're not going to get e to the negative 5t. So they are linearly independent of each other. And we have a way of checking that for general functions in the next section, I think. Yeah. So this is what my general solution looks like. And I'm going to pause for a moment. Yeah, what I really want to do is I want to check, first of all, and see that these two, e to the minus 5t and e to the 2t, are in fact solutions to the differential equation. So here's the e to the minus 5t first, so I plug it in. I'm going to take its second derivative, I'm going to take its first derivative times 3, and I'm going to add that. And I'm going to take, this doesn't look like an exponent, does it? Yeah, that's better. Taking the second derivative, the minus 5 comes out twice, giving me a 25 right there. Taking the first derivative, the minus 5 comes out once, so it's minus 3 times 5, e to the minus 5t. And then I didn't do anything here, just left it alone. But notice, 25 times this exponential, minus 15 times that exponential, minus 10. 25 minus 15 minus 10, that's 0. That's 0. So yeah, this is a solution. Likewise, when you plug the e to the 2t in, e to the 2t, take the second derivative, times 3 e to the 2t, take the first derivative, minus 10 times e to the 2t. So the second derivative, the 2 pops out twice, leaving a 4 there. The first derivative, the 2 pops out just once, leaving 3 times 2, which would be a 6. And so I've got 4 times this exponential plus 6 times that exponential minus 10 times the same exponential. 4 plus 6 minus 10, 0. Okay, so yeah, these are both solutions. So any scalar multiple of them is a solution, and any sum of those scalar multiples is also a solution. Right? So now what I want to do is I want to find the right coefficients to satisfy the initial conditions. Remember, my initial conditions were that the function at 0 is 3 and the derivative at 0 is 4. So here we go. In order to use that second derivative, I'm going to need to know what the derivative is. So this is what I said y was equal to. And so when I take the derivative of that, the minus 5 is going to pop out, and the 2 is going to pop out, so I get this right there as my derivative. Okay, so here we go, plugging into the initial conditions. The first initial condition, I'm plugging into the function. So I'm plugging a 0 in for t here, and it's supposed to equal 3. Right? So there's that, which gives me the equation. Plugging a 0 in, e to the 0 is 1. So I got 3 equals c1 plus c2. Likewise then, for the second initial condition, they're talking about the derivative, so I'm plugging a 4 in for the y prime and a 0 in for t in this equation, getting this, and again, the e to the 0s are 1, so 4 is equal to minus 5c1 plus 2c2. What I have here is a system of 2 equations in 2 unknowns. Solve them how you see best. Some people do substitution, some people do elimination. Personally, I would multiply this top equation by 5, get 15 equals 5c1 plus 5c2, and then add the equations. The 15 plus 4 is 9, the c1s cancel out, and the 5c2 plus 2c2 is 7c2. So 19 equals 7c2, and c2 is equal to 19 over 7. Likewise, I would multiply this top one by negative 2 and get negative 6 minus 2. Anyway, the 2's cancel out and you get that c1 is 2 over 7. And there's the solution, right? That having those 2 initial conditions allows us to find both constants c1 and c2. To say, here's the particular linear combination of e to the minus 5t and e to the 2t, which guarantees that we're a solution to the Differential equation, and we found the right constants to also be to satisfy the initial conditions. In general, this is a reasonably quick process because you don't have to do all these steps necessarily. You need to get to the quadratic equation here, solve it for R1 and R2. That gives you the general solution here, and then use that general solution to find the constants to satisfy the initial condition. So there you go, an example of second order homogeneous with constant coefficients.